light and matter.
Right. So we have the interaction between light and matter. And so with respect to IR spectroscopy, what were we looking at specifically? We're looking at how light interacted with what parts of our organic molecules, or what parts of compounds. We're dealing particularly with
Bond strengths.
Bonds, right? So we were dealing with bonds. Most importantly, what were we dealing about with respect to bonds? Not necessarily strength, but stretching frequency, right? The vibration frequency of bonds, okay? So again, with respect to bonds, we're dealing with electrons, etc., okay? Now, with respect to IR, what was the general region of the electromagnetic spectrum that were we looking at particularly with IR spectroscopy?
So wave number and
wave number. So what part of the electromagnetic spectrum, right, where we have all the way from radio waves all the way to gamma rays, what were we looking at with IR? What type of light? Infrared, right? So that's what the IR stands for. We're looking at infrared light, okay? And again, infrared had that energy that was equivalent to those vibrations in our bonds, okay? Okay, so that was IR spectroscopy. We are going to continue on today by talking about another spectroscopy, which is slightly different than IR spectroscopy. And the spectroscopy that we're going to talk about today is called NMR. Okay, so NMR stands for nuclear magnetic resonance. Okay, so nuclear magnetic resonance. What does that mean, right? So number one, with respect to NMR and nuclear magnetic resonance, we are not going to be looking necessarily at electrons, right? Instead, we're going to be looking at the nuclei of atoms. So what's in the nucleus of an atom? So we have in our nucleus, so we've got our nucleus, we have our protons, and then what else do we have in our nucleus? Neutrons, okay? So just as a note, with respect to protons and neutrons, protons, what is their charge? Positively charged particles, right? So we've got our positively charged particles. What about neutrons? No charge, okay? So zero charge, charge neutral, okay? So nuclear magnetic resonance deals with the interaction between light and nuclei. But what is that? Where are we getting this at, right? What does light even interact with nucleus to begin with, okay? So I'm going to explain this by actually going back to electrons to kind of explain the idea behind what happens in the nucleus, how the nucleus has what's called a magnetic moment, and where that actually comes from, okay? So if we go back and think about electrons, electrons are charged particles as well, right? So what is the charge of an electron? Negative charge, right? So we have a negatively charged particle when we're dealing with an electron, okay? Now, if we go back to quantum mechanics, right, we had talked about the fact that electrons have what is called spin. What was that? What was electron spin? Or what were we trying to model with this idea of electrons spinning? So electrons spin, and what we had said in our little model is that you can imagine them as little tops, right? Little tops and they're spinning, right? The big thing that came out of that, though, was that there was what was called a spin moment, right? And so for electron spin, we represented that as m sub s. This guy could only take on one of two possible values, right? What was that spin quantum number? It could either be plus 1/2, or what is the other possible value that the spin quantum number m sub s could be? Minus 1/2, right? It was quantized. It can only have one of two possible values, plus 1/2 or minus 1/2. And the way we imagined that was that this little electron, because it's a charged particle, and this is one of these laws of electricity and magnetism, if you have a charged particle and it's moving and it's spinning, it's creating its own little magnetic moment, its own little magnetic field, okay? And for the electron, we said, well, that field can only have one of two possible values. It could either have spin up, right, and we call that maybe spin north pole, or it could have spin down, spin south pole, okay? So again, electrons are spinning charged particles. They create their own little magnetic fields, okay? Now, what about a proton? So protons, are they also charged particles? Yes. So protons are positively charged particles, right? So we can draw them as a nice little positive charge. Again, they're in the nucleus of our atoms, okay? What we haven't let you guys know about at this point in time is that they also are spinning. We can imagine them spinning like little tops on their heads, okay? So if we have a charged particle that is spinning, will it also create its own little magnetic field? Yes. Okay, so this is a big, big thing with respect to NMR spectroscopy. So protons also create their own little magnetic field. Just like electrons, it can only take on one of two possible values. It could only take on what we'll call spin up, or it could take on what we'll call spin down. And again, we can imagine this like a little bar magnet, right, where we have a north pole and a south pole, and it can only be either north pole or south pole, okay? Okay, yes?
Does it spin the same direction as an electron? Did you mention it spin up and spin down?
Okay, so it doesn't really spin, and that's something that we don't really want to get into. The way we model it in our head is that it is spinning, right, like a top, but again, it's either spin up or it's spin down. So imagine it like that. It either spins one way or it spins the other, and it doesn't spin both at the same time. Okay, so that's great. Okay, so we have a nucleus, we have protons in the nucleus, right? They are spinning, they're creating their own little magnetic moment, okay? Now, a big thing with respect to this is that to have a net overall magnetic moment for our nuclei, we have to have an odd number of protons and neutrons in the nucleus, right? To be NMR active, you have to have a net magnetic moment, and that net magnetic moment comes from having an odd number of protons and neutrons in your nucleus, okay? So we think about hydrogen, and the most abundant form of hydrogen, which is what we call hydrogen 1, right? What does hydrogen 1 have in its nucleus? It has, if we go back to the atomic number of hydrogen, it has 1 proton, right? But then how many neutrons does it have?
0.
0, right? So the most abundant form of hydrogen just has a proton in the nucleus. It has 0 neutrons. So when we add those together, is that an odd number? Yes. So that means that hydrogen, which is one of our most abundant of elements that we use in organic chemistry, has a net magnetic moment, is what we call NMR active. Okay? What about carbon? Because carbon is another very abundant atom that we use in our organic compounds. What is probably the most abundant isotope of carbon? 12. So carbon 12. Carbon 12 has 6 protons, and then it has 6 neutrons in the nucleus. So is carbon 12 NMR active? Does it have a net magnetic moment? No, because again, when we sum these guys up, we get an even number. So there is no magnetic moment. And so we are NMR, let me write this out better, moment, we are NMR inactive. Which is unfortunate because carbon is very, very common with respect to even number is going to lead to we won't have any magnetic moments, so we're not going to be NMR active if it's even. Yes.
Why is there a 3? What is a 3?
Oh, no, it's
Oh, okay.
together.
Oh, yeah, that's my weird summing together, combined squiggle, yeah. I'll get rid of that guy. Okay, so proton, NMR inactive, good. Hydrogen, right? Hydrogen nuclei. Carbon 12, NMR inactive, because again, we have an even number. Another isotope of carbon, though, that we'll find is something called carbon 13, right? So about 1% of the time, this carbon 13 will be in our molecules. So for carbon 13, we still have the 6 protons. But now how many neutrons does carbon have if it's carbon 13, that isotope? 7, right? So again, the mass number here is the sum of the protons and the neutrons. So carbon 13 has 7 neutrons. So again, when we add them together, overall we get 13, which is an odd number. So is carbon 13 as an isotope NMR active? It is active, okay? So we would have this guy that is NMR active. We do have a net magnetic moment for carbon 13. Okay, so for organic chemistry, when we teach NMR, we focus pretty heavily on this guy, this H1, and we will also focus at the very end of the chapter on carbon 13, because these are the atoms that are actually going to have net magnetic moments that are going to be NMR active, okay? Okay, so carbon 13 is one. Another thing that I call this very frequently, so this is called H1 NMR. when we deal with the hydrogen nuclei that we're looking at. This is also called proton NMR. So those words, H1 NMR and proton NMR, are the exact same thing. They're referring to the exact same type of NMR. We're looking at the nuclei of hydrogen that are in our compounds. Okay, so that's some logistics, things that we're going to focus on, H1, carbon-13. We've just now talked about how hydrogen has a net magnetic moment in its nucleus because it has a proton. That proton is this charged particle, it's spinning, creating its own little magnetic field, okay? Now, let's imagine that we took a collection of just hydrogen atoms by themselves, right? So a collection of hydrogen atoms, and let's say we had them in a tube, okay? And we took them, and to them we applied a very, very, very strong external magnetic field, okay? So I'm going to abbreviate this external magnetic field as this B naught, okay? So again, this is a very strong external magnetic field. So if you imagine these guys as tiny little bar magnets, right? And you take these tiny little bar magnets and you apply a really strong magnet to them, what are they going to do?
Repel?
So some of them will repel, right? But some of them will do what? Be attracted to it, right? Because again, they only have one of two possible ways, right? They have a north pole and they have a south pole, okay? So it's the exact same thing here. We have a collection of hydrogen atoms, right? Their nuclei have their own little net magnetic moment. When we apply an external magnetic field to that, they're either going to align with the field, right? So they're going to have themselves aligned with the field, or they're going to align against the field, okay? So this only happens when we apply this external magnetic field to it. They align either with the field or they align against the field, okay? Now, these two possibilities of being with the field or against the field have different energies, and this is the big idea behind NMR spectroscopy. So if we drew this using our little common energy diagram, where we have energy on our little y-axis, right? We have our little net magnetic moments, right? We apply our little magnetic field. Who do you think is going to be at a lower energy state? The nuclei that align with the field, or the nuclei that are repelled and align against the field?
How does it repel?
The one that goes with it.
Okay, so it ends up being a little bit lower of an energy state is the one that aligns with the field. Okay, so this guy is with our field. We call this what is called the alpha spin state. And then at a tiny, tiny, tiny little bit of a higher energy state, we have our nuclei that align against the field. And we call that our beta spin state, okay? So this is the basic understanding of NMR spectroscopy. When we apply an external magnetic field to these nuclei, some align with, some align against, there is a difference in energy between whether or not they align against or with, right? And it's this difference in energy that we're essentially trying to utilize in our spectroscopic technique, okay? Okay, so again, we have our alpha spin state, our beta spin state. We have nuclei that are in alpha and some that are in beta. So now let's imagine that we shine in light that has an equal energy that is equal to this difference in energy between these two spin states, right? If we do that, we have a light source out here. We've got our difference in energy between our two spin states, and we shine in light that has equal energy. What's going to happen? So equal energy, light has equal energy. We have this difference in energy between the two spin states. If I shine in light, what's going to happen is one of our little alpha spin state nuclei is going to be promoted, and it's going to undergo what is called a spin flip. Okay, so it's the same exact thing with vibration, same exact thing. If you shine in light with energy that is equal to that energy difference between the two spin states, you're going to get absorbance, right? And in terms of NMR, what that means is this guy is essentially going to be promoted to the beta state, and he's going to flip his spin. So as a reminder, with respect to light or energy of light is always equal to h nu. What does h stand for? H nu. What was h? That was a constant, right? Planck's constant. We don't really care about it. We really just want the understanding between energy and what is nu? What does nu stand for? I know it looks like a V. Frequency, right? So again, the relationship between energy and frequency is directly proportional, right?
Okay, when you said that there's, if you shine light with energy, that's equal to the, if you shine light with energy, that's equal to the energy difference between alpha and beta. The alpha gets promoted to beta, so it does a spin flip, so it changes it to a beta, or it acts like one. You understand?
It flips its spin. So imagine it's going one way, right, and creating that magnetic field. If it absorbs that energy, it'll start rotating the other way and creating the other magnetic field.
Okay, so it turns into a beta?
Yeah.
Okay.
Yeah.
Oh, it transforms, okay.
But again, what we're going to see is when we shine in light to whatever sample that we're looking at, right, if that light gets absorbed by flipping alpha to beta, then we're not going to see it come through, right? And so that's the whole idea behind spectroscopy. The stuff that gets absorbed because of these energy differences doesn't come through, and we see that as absorbance in our overall spectrum. Okay, so that's the basic idea, right? We have these magnetic moments in our nuclei. The minute we apply an external magnetic field to them, they're going to separate into alpha and beta. We take our little sample, we shine light in of different frequencies, and we find the frequency that matches the energy difference between alpha and beta. We get absorbance there that shows up in our little overall NMR spectrum as absorbance, okay? Now, a couple more things to note. With respect to this energy difference in between these two spin states, this energy difference is very, 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 very small. Very tiny energy differences, okay? So much so that the frequency of light that we use in NMR spectroscopy ends up being at the radio wave wavelength of the electromagnetic spectrum. Okay, so we're going to be dealing here with very, very, very small frequencies, very large wavelengths. We're going to be dealing with radio waves in terms of the energies that we're looking at. Okay? One other thing to note, okay? So this was our nice little external magnetic field, right? We can vary that magnet, right? So let's say that we had a magnet that had a strength of 1.4 Tesla, right? So we're not going to talk about Tesla, that's just an overall unit for magnetic field strength. But let's say that we had that and we split these guys into their two different spin states. If we increase that magnetic field to something like, let's say, 7 Tesla, the difference in energy between alpha and beta is going to get larger. Okay, so the overall stronger the magnetic field, the larger that energy difference, the larger frequency at which we will absorb light. So if we're at, let's say, 7 Tesla, that difference in energy between alpha and beta gets very large comparatively. So again, what we're going to see here is we're going to see light absorbing at a higher frequency due to this larger energy difference. Okay, so that's a big overall correlation. The stronger the field, the larger the energy difference, the higher the frequency of light we're going to actually absorb. Okay, that's the basis. Okay, magnetic field, energy difference between the two field states depends on the overall magnetic field strength that we're applying. The larger the magnetic field, the larger the energy difference, the higher the frequency of light that we will absorb. Okay, now, that was a sample of just hydrogen nuclei, all right? So we haven't even gotten to the point where we're actually dealing with things in a compound, okay? Now, if all hydrogen nuclei reacted the exact same way, we're in the exact same environment in compounds, then NMR would not be very useful, okay? Because if all hydrogen nuclei had the exact moment, felt the exact same field strength, then all we would get is one radio frequency at which we would absorb light. And that wouldn't be very useful because, again, the entire purpose of spectroscopy is what? So IR, we dealt with functional groups and figuring out what type of functional groups are present, but the entire purpose of this is structural determination. We want to figure out what is the structure of our molecule, okay? NMR as a spectroscopy or as a technique is the most powerful structural determinant or determiner that is out there, right? It is the most powerful technique for overall structural determination, and I'll hopefully illustrate why that is as we go through this chapter, okay? Now, again, if we just had a sample of hydrogen nuclei and they weren't being influenced by any other source, we applied a magnetic field and we shone in light, or we shined light onto that overall sample with that magnetic field, all we would see is absorbance at a certain frequency, and that would be it. And it would be fairly non-useful with respect to structural determination. There are other factors, though, that are going to go into actually helping us to figure out what's going on in this overall molecule, okay? So let's imagine that we have something like methane, right? So we have methane versus something like trifluorocarbon, whatever this guy is. I don't even know the name of this, okay? Trifluoromethane, something like that, okay? All right, so again, we're looking at hydrogen, and that's a big thing that you have to know. We're looking at NMR, we're looking at hydrogen nuclei, okay? So let's imagine that we had this sample of hydrogen nuclei, and we were wanting to look at NMR for this hydrogen nuclei specifically, okay? So again, all we'd have to do is apply an external magnetic field that's fairly strong, right? It's going to bring that hydrogen nuclei into the alpha and beta state, and we're going to shine in light, and we're going to figure out, hey, where are we actually going to see absorbance at, okay? Now, there's another big thing that's going to influence where this guy actually absorbs light and the overall magnetic field that it actually feels, okay? And that goes back to the presence of electrons, okay? So again, we're looking at the nucleus, right? So what's in this bond right here?
Here's carbon.
So what is in this guy? What is it? What do we represent as a line? What is that supposed to be? It's what? Single bond, but what's in a bond? Electrons. Electrons, right? So electrons are in bonds, right? So we're saying, hey, we're looking at this hydrogen nuclei, but it's kind of close to all these electrons that are in these bonds, okay? So again, electrons are charged particles, right? And going back to the laws of electricity and magnetism, the minute you apply an external magnetic field to a charged particle like an electron, it is going to begin to rotate, right? So it's going to start to move, and it's going to start to move in a way that opposes the external field. It's going to make its own little magnetic field that opposes the field that you're actually applying, okay? So you have this big, strong magnet, right? It's here, it's doing its thing, right? This guy, our little nuclei of hydrogen, feels that magnet. But also what's happening are these electrons are starting to circulate in a way that make their own little magnetic field that opposes that external magnetic field, okay? So this nuclei, because of that, feels the external magnetic field, but it also feels this guy, and I shouldn't use a line here, which is what we're going to call this local field, this beta local, okay? Okay, so this is the big difference, right? We have external magnetic field. These electrons start to circulate in a way. They create their own little magnetic field that opposes that external magnetic field. So because of that, does this hydrogen get to feel the full strength of this external magnetic field?
No.
No, right? Because it's feeling both this guy and this guy. The combined effect is essentially a reduced field that it actually feels, okay? So this process is something called shielding. The electrons are shielding the nuclei from feeling the full effect of that external magnetic field. And so because of that, this guy feels less of beta naught. So again, this is shielding. Shielding. And this overall effect of putting an external or putting a magnetic field onto things like electrons and them making their own little magnetic field, that thing is actually called diamagnetism. And it's kind of the basis behind this idea of being able to levitate. In theory, if we have electrons in our body, right, if we had a strong enough of a magnet, all of our electrons would begin to circulate, creating their own little magnetic field that opposes that field, and eventually we would create strong enough of a field that we could actually levitate off the ground. There's no such thing as that strong of a magnetic field yet. We can't actually create that strong of a magnet, but it is possible in theory.
So I can fly.
You could fly, yes, if we had a strong enough magnet. Okay, all right, so shielding, right? Presence of those electrons. because that guy feels less of a magnetic field, this hydrogen is going to absorb light at a little bit less frequency, right? A little bit less energy because it's feeling less of a magnetic field, okay? Now, let's compare that to this guy over here, this hydrogen, okay? Same exact thing. We want to look at this hydrogen via NMR, okay? We apply our external magnet. So we go ahead and apply our strong external magnet to this guy. And again, the electron density that is in the bond right next to this hydrogen is going to start to circulate. Right? It's going to start to circulate, and it's going to create its own little magnetic field that opposes that external magnetic field. Okay? What's the difference here, though? How much electron density is actually present in this bond versus this bond over here?
Oh, it's gonna be less because of the induction, right?
Right, so here, this carbon is surrounded by 3 different fluorines. Fluorines are really electronegative, right? What does that mean in terms of what they're doing to the electrons that are in those bonds? So these guys are all pulling the electron density towards themselves, pulling it towards themselves, pulling it towards themselves, right? So because of that, the electrons that are present in this bond is not as much comparatively to the electrons that are present in this bond, okay? Because these guys, these are not electronegative. These are all nonpolar bonds, so those electrons are really there. They're really present, okay? Because this guy is pulling that electron density away, there's less electron density in here. So we have less electron density, which in turn means that even though those electrons are still circulating, they're not going to create as strong of a magnetic field to oppose the external one, right? So this guy, let's say he created a really strong external magnetic field. This guy's only going to create a slightly tinier magnetic field to oppose it, okay? So then because of that, because this little local field, beta local, is smaller than this beta local, this guy gets to feel a much stronger influence from this overall, from our external magnetic field. Because it feels more of this guy, it's got a larger energy difference between its 2 spin states, it's going to absorb light at a higher frequency because of that. Okay, so this idea behind induction, this idea behind protons being in different chemical environments is going to actually take a role or take effect in the overall NMR spectrum. So if we went ahead and said this is going to be called hydrogen A, and this is going to be called hydrogen B, when we look at our NMR spectrum, what we're going to find, if we're increasing in frequency, going from right to left, is that hydrogen A would absorb at a lower frequency than hydrogen B. This would be hydrogen A, this would be hydrogen B, because again, it feels less of that magnetic field than hydrogen B comparatively. So this is the basis behind NMR. Yes?
I was just wondering, why did you kind of put HA and HB in like those blocks?
So I'm saying that because these guys are in different electronic environments, they're going to absorb light at a different frequency because they're feeling different magnetic fields, right? This guy feels more of this external magnetic field, meaning its energy difference is going to be larger, meaning it's going to absorb at a higher frequency comparatively to this guy. Because this guy is being shielded, right? He's got all these electrons near it. It's creating a really strong opposing magnetic field, so it doesn't feel as much of this guy as a result. This guy feels more of this larger energy difference, larger frequency.
Are those kind of like peaks?
Those are peaks, yeah, and we'll talk about what they actually look like in the next slide. So when we're looking at NMR spectroscopy, we are looking now at absorbance again. So instead of IR, where we're looking at percent transmittance and troughs, we are looking at peaks for our signals here. Okay, is that the basics, right? I haven't missed anything. External magnetic field, this is the basis behind, we're increasing frequency, going from low to high. And this is what we're going to be able to do with NMR spectroscopy. Yes?
So I'm assuming this is now de-shielding?
Yes, this is de-shielding.
Okay.
So shielding is what happens when these protons are around a lot of electrons, right, because there aren't a lot of electronegative elements present. De-shielding is the opposite of that. It's when you have a bunch of these electronegative elements that are essentially pulling those electrons away and de-shielding that proton so that it can feel the full effect of the external magnetic field.
And it'll always have a higher peak.
It will always, not higher peak, these are actually equivalent, and we'll talk about what
Higher
these,
frequency, I'm sorry.
higher frequency, yes. Okay, so that's the basis. So now we're going to go about talking about real NMR, what it actually looks like, and what we can gain from a spectrum. How we're going to actually utilize this type of information to track back and use that to determine the structure of our molecule. Okay, so we're going to go through this in a very set, formulative, or not formulative. I'm searching for words today, but. Yeah, okay, so we're going to go through the various features of NMR spectrums to understand exactly what they're telling us at each different point in time, okay? So the first thing that we're going to focus on is the actual number of signals, okay, and I'll explain what I mean by a signal, as well as their location. These kind of go together. This is something that we're going to call chemical shift. Afterwards, we're going to talk about the actual area under each signal, so what we call an integral, and then after that, we'll talk about the overall shape, which is what we're going to call a splitting pattern, okay? So this is an NMR spectrum. This is a proton NMR, right? What I'm looking at here is essentially all of these peaks correlate to what we're going to call a signal, right? So this guy is a peak. It is what I'm equivalating to a signal in our spectrum, okay? So if I look at this spectrum, I find that I have a jumble of peaks here, a jumble of peaks here, a jumble of peaks here, right? What I would consider this is three separate signals or three separate peaks, okay? So this guy would be a peak, call this peak number 1, this would be peak number 2, this would be peak number 3, okay? So the first thing we're going to talk about is what's giving rise to these different numbers of peaks, right? These different numbers of actual signals. The second thing we're going to talk about is why they're located where they're at, right? So this is what we talk about in terms of chemical shift. The third thing is what I mean is the area under the signal. It's what I call the integration. So if I were to go through for this signal, for example, and I were to integrate under our little curve here, I would actually be able to tell the number of protons that actually give rise to that signal. So that's what I mean by integration. And then finally, signal shape. So sometimes we're going to find that we just get a single peak, and that's great. But if I look at this guy right here, how many different peaks are actually in this signal? 4, okay? So that distinct feature is going to give us a lot of information about the overall area surrounding the proton that's giving rise to the signal. Okay, so even though there's 4 peaks, that's still just one signal. We're going to talk about what creates those 4 peaks at the very end of this. Okay, so the first thing we're going to talk about is just number of signals. How do we know how many signals we're going to expect in our NMR spectrum? Okay, so overall, what we're going to find is that protons that are in similar chemical and electronic environments are going to give rise to the exact same signal in the NMR spectrum. Okay, so what do I mean by that? So let's say that we have something like propane. Right, so 3-carbon propane, okay? With respect to NMR, and H1 NMR, which is what we're focusing on, who are we actually looking at in this molecule? The H's, right? Are they drawn on here? No. So that's number 1, right? We're looking at H's, and usually in the molecules that are going to be given, they're not going to be drawn on, they're actually going to be implied, okay? So now, how many different H's do we have to consider in looking at the overall molecule or the structure of propane? So we have 1, 2, 3 here, right? We've got 1, 2 here, and we've got 1, 2, 3 here. All right, so there are 8 total protons that we're looking at, okay? Now, the question is, well, how many different signals or how many of these guys are actually in distinct electronic environments, right? If they aren't, if they're in the exact same chemical and electronic environment, we call them chemically equivalent protons, and they're only going to give rise to 1 signal overall, okay? So for right now, I'm only going to focus on these 2 protons in the middle and trying to explain how to determine whether or not these are actually chemically equivalent, or whether they are different overall protons. They would give rise to different overall signals, okay? Now, to explain this, I'm going to go back to our symmetry operations that I had introduced back in Chapter 5 with respect to stereoisomers, right? So in Chapter 5, I said there are two different types of symmetry operations that we're going to focus on. There is rotational symmetry, and there is reflectional symmetry, right? So what was rotational symmetry? So with rotational symmetry, if you had a molecule, let's say you skewered it right down the middle, right? And you closed your eyes, and you rotated that molecule, and you opened your eyes again. If it had rotational symmetry, could you have told whether or not you had actually rotated it? No, it would look the exact same, okay? So for this guy, for our little propane molecule, if I skewer it and I rotate it 180 degrees, can I tell that I've rotated it? No. So these guys, because of that, are chemically equivalent protons. They will give rise to the exact same signal because they possess rotational symmetry. So these guys are chemically equivalent. Let me write that down, equivalent. Even though there are two of them, they're going to only give rise to one signal. And that's because they possess rotational symmetry. Okay, so anything or any proton that does possess this rotational symmetry, they're called homotopic protons. So this H, we'll call this HA and HB, are homotopic protons. And then one surefire way to determine whether or not something is a homotopic proton. So for example, let's say I had this molecule down here where I was questioning whether or not these guys were chemically equivalent. One easy way to do this is to do what's called a replacement test, okay? So in a replacement test, what I'm going to do is I'm going to take one of these protons, I'm going to replace it with deuterium in one molecule, and in a second molecule, I'm going to take the other proton, I'm going to replace it with deuterium, okay? When I do that for this guy, because this guy does possess rotational symmetry, what do I get as a result? Are these different compounds? No, these are the same compound. So if you have homotopic protons and you will do the replacement test, you're always going to get the same compound as a result. That tells you that those protons are homotopic, that there is a rotational symmetry element for this molecule. And again, they're chemically equivalent as well. Okay, so that is rotational symmetry and homotopic protons. There is one other symmetry operation, and what was that? Besides rotational symmetry, there's reflection, right? So let's imagine that instead of dealing with propane, we are now dealing with ethanol. Okay, so we draw out bond line structure of ethanol. We've got this guy. And again, we're not looking at the carbons or the oxygens. We're looking at whether or not these two protons, we'll call this HA and HB, are chemically equivalent or not. Are these the exact same proton? Are they going to give rise to one signal? Now, for this molecule, do we have rotational symmetry? No. If I skewer this and I rotate it, I can tell the fact that I've rotated it. Okay? What do we possess now instead, though? We don't have rotational symmetry, but if I passed a mirror through this molecule, if I slid it in half with a nice mirror plane, and I reflected this side over to this side, could I tell whether or not that reflection had occurred?
Wait, what? If you just
So if I slice this molecule in half and I reflected this side over to this side and vice versa, could I tell whether or not I did that after looking at it?
No.
No, right? Why? Because this guy, instead of having rotational symmetry, has reflectional symmetry, right? Instead of an axis of rotation, it now has a plane of symmetry, okay? So those are two different symmetry operations. Regardless if it has reflectional or rotational, they are still essentially chemically equivalent protons, right? So these guys are chemically equivalent because they possess a mirror plane as opposed to an axis of rotation. Chemically equivalent, so again, one signal. And so again, a nice little easy way to test this, instead of having to figure out whether or not there's a mirror plane, you can do this and that, is to do the replacement test, right? If these guys have a mirror plane, instead of being called homotopic protons, they are now called enantiotopic protons, okay? If they have that reflectional symmetry. If you do the replacement test with enantiotopic protons, where you replace one with deuterium and then the other with deuterium, the two new molecules that you get are not the same compound. And now, what are they instead? They're enantiomers, okay? So if you have enantiotopic protons and you do the replacement test, you will get enantiomers as a result, as opposed to the same compound, which would lead from homotopic protons. Okay, so that's good, right? This one, he didn't have rotational, but he did have reflectional. So again, these protons are chemically equivalent. They will only give rise to one signal. Now, what is the situation where this wouldn't occur? Where you have these two protons that are on the same carbon, and they wouldn't have rotational and they wouldn't have reflectional. So for example, what about this molecule? Again, I'm looking at whether or not these two protons are chemically equivalent or not. Whether A and B are going to give rise to one signal or multiple signals, okay? First question I'm going to ask, do we have rotational symmetry in this molecule? If I rotate this molecule, can I tell that I've undergone that rotation? Yeah. Yes. So we don't have a rotation axis, so we don't have homotopic protons. What about reflectional symmetry? If I pass a mirror through this molecule, if I bisect this molecule with a mirror plane, and I rotate, or not rotate, but I reflect this side onto that side, can I tell that I've done that? So if I did that, if I went ahead and drew that out, and I imagine we can draw the hydrogens here, but if I reflect this onto the other side, what am I going to get instead? It's not going to be coming out at us. It's going to be going into the board, right? So again, this is what I mean by this reflectional symmetry. If I reflect this side to that side, will I get the same thing? No, okay? So this does not have a reflection or a mirror plane either, okay? So it's not rotational, it's not reflectional, right? So they're not homotopic, they're not enantiotopic. So because of that, these two protons are chemically non-equivalent. They will give rise to two separate signals because they're not chemically equivalent now. They don't have rotational axis, they don't have reflection, mirror plane. So these guys are chemically non-equivalent. They're distinct. Non-equivalent. So because of that, for these two protons, we would get two separate signals. Okay, so for this molecule compared to the other two, what's the big difference? What have we introduced in this molecule that wasn't present in the other two that have made these now chemically non-equivalent?
The extra signal.
The wedge turned to a dash.
What was this, though, that made that wedge turn into a dash? What is this called, this carbon that contains that?
Chiral.
Right, so the big difference here was that this molecule had a center of chirality, right? And so that turned these two protons, instead of being just chemically equivalent, that made these two chemically non-equivalent, right? So a chiral center is going to take protons like this and produce two signals as a result.
A chiral center always is going to have two signals.
It depends. There can be other aspects of rotation and reflection that we have to consider, but in a situation like this, yeah, the presence of that chiral center turns those two protons into two signals. Okay, so for these guys, these are not homotopic protons, these are not enantiotopic. Instead, if we did the replacement test with these two, we wouldn't get enantiomers, we wouldn't get the same compound, but what would we get instead? Diastereomers, right? So these protons end up being called diastereotopic because the replacement test produces diastereomers, and again, they're not chemically equivalent. Okay, so that's a lot of information to go into and just trying to determine the number of signals in an overall molecule. So we're going to take that, what we just learned, and we're going to couple it with a couple of nice little caveats. caveats to remember moving forward, okay? First one, and this is probably the most important one, is any type of methyl proton. Those guys are always going to be chemically equivalent, okay? So what do I mean by methyl proton? If we go back to our nice little ethane or butane, no, propane, pardon me. Methyl protons, so these guys are all chemically equivalent with respect to one another. So these three would only lead to one signal. And for methyl protons, that's always going to be the case. They're all three of them going to only produce one signal. Now, after methyl, we would look at something like this guy. This is a CH2. This is what we call methylene protons, right? So methylene protons are these CH2 groups. They will also be chemically equivalent and produce only one signal as long as there isn't a chiral center in the molecule, which is what we just demonstrated. What we were just looking at was methylene protons and whether or not they were chemically equivalent. So these guys will always be chemically equivalent as long as there is no chiral center. And then finally, if the entire molecule can have protons that are exchanged by either rotation or reflection, then you'll have multiple protons that are actually chemically equivalent to one another. So what I mean by that is illustrated in this molecule over here. Let me draw this better. Right, so again, we're looking at the protons and determining how many different signals we would get. How many different protons am I looking at for something like this?
3. No, 2.
So we've got this set of 3. We've got this set of 2, this set of 2, and this set of 3. So notice that these methyl protons, we've already said methyl protons are always equivalent. So we could say, okay, these 3 are going to give rise to one signal, right? So one signal. We can call these guys HA. We also just said that methylene protons will give rise to one signal as long as there's no chiral center. For this molecule, is there a chiral center in this? No. So these 2 would be one signal as well. Okay, so we'd have one signal from this guy. But now, even though these are at different regions of the molecule, can these guys and these guys be replaced via one of our symmetry operations? If I took this molecule and I rotated 180 degrees, can I tell whether or not I'd exchange these two? No, right? So because of that, because both this set and this set can be exchanged as well as this set and this set, these methyl protons over here are chemically equivalent with these guys, and these methylene protons, are chemically equivalent with these guys. So overall, for this molecule, even though there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, however many protons there are, there's only 2 signals. Because these guys and these guys are chemically equivalent. They can be exchanged via rotational symmetry. And these guys and these guys are chemically equivalent. They can also be exchanged via rotation. So 2 and 2. Well, it'll be 1 and 1, but why? Why would you do that to me?
And when we talk about signals, we're not talking about the 4 and 1 set.
No,
talking about
we're
two
just
different-
we're talking about there's a signal over here and there's a signal over here. Why? Why would you do that?
Is that a lady left?
System is warming up. What?
Is that lady left?
Yeah, Marianne.
Oh, she lives by there?
She left pretty early.
She probably doesn't understand what we're talking about.
Like, I'm wondering, what is she
Yeah.
here for? The ballerina?
Yeah, I get evaluated ad nauseum all the time. It's the first time you guys have had to put up with it. Okay, so with that, I actually want us to do an example problem. And it's going to come up on here, but I'll go ahead and put it on the board so you guys can work on it. So, again, I'm looking for the number of chemically equivalent protons in each of these two compounds. So the first one is this molecule, right? So I want to know how many distinct signals or how many chemically equivalent protons we actually find in this molecule. And then the second one is this guy. Okay, so we didn't do this example in class, but I did include it in the PowerPoint, so I wanted to go ahead and go through it. So in this type of problem, we're looking for the number of chemically equivalent protons in each of these following molecules. And again, each set of chemically equivalent protons is going to give a separate signal in our spectrum, right? So depending on however many sets of these chemically equivalent protons we have, is essentially going to determine how many signals we're going to find in the NMR spectrum. So we're going to start with this first molecule right here, right? And so we're going to use some of the kind of like guiding principles that we ended on that last slide. So one of those was that all methyl groups, so all methyl protons, all of these guys are always going to be chemically equivalent, right? So if I start out here on the left side of my molecule, I know I have 3 protons here. These guys are all going to be chemically equivalent with respect to one another, right? So this would be what we'll call set A. Then it also told us that methylene, so this is CH2 groups, this is what we call a methylene proton. These guys are also going to be chemically equivalent as long as there is not a chiral center in the molecule. And if we look at this molecule, we'll find there is not a chiral center. So this set of protons will also be its own set of chemically equivalent protons. So these guys will be what we'll call B. As we move down, we get more protons. So these guys will also be chemically equivalent with respect to each other, but they are different and distinct from this other set of methylene protons, because again, we're looking for similar electronic environments. And note that these protons are much closer to the bromine comparatively to these protons, right? So green and blue are not chemically equivalent with one another, but they are chemically equivalent with respect to each other, right? So we have our set here. This guy will be called C. So both of these guys will give rise to the same signal. And then as we move on, we have one last set of protons, right? So we've got a bromine attached to this guy. This is directly attached. So again, these two are going to be chemically equivalent to one another, right? So these guys would be D. So we'll call this D and D, but they're going to be distinct and different from our set of C protons as well as our set of B protons, okay? So in this overall molecule, we get an A, we get a B, we get a C, and we get a D. So overall, there are going to be 4 separate signals in the NMR spectrum, okay? Okay, so now we're going to move on down to, we'll say, molecule 2. Again, I'm going to start with those kind of like guiding principles that we had before, right? So the first set I'm going to look at are these guys out here. These are our methyl protons. And again, what we've already determined is that methyl protons are always chemically equivalent with each other. So we'll go ahead and call this Ra. We'll then move on to these guys. So again, methylene, these are methylene protons. They are also going to be chemically equivalent to each other as long as there isn't a chiral center. So there is not a chiral center in this molecule, so this will be a second set. As I move on, I'll find at this position there are no protons, there are no H's. At this position there are no H's. At this position there are no H's, right? So we can essentially ignore both of those. There are no H's here, but there are H's out here on the methyl group, right? So we've got some methyl hydrogens, methyl protons right here. So these are not symmetric with any other portion of the molecule, so they're going to give their own separate signal. But again, they're only going to give rise to one signal together. So these would be a third set of chemically equivalent protons. And then as I go over here to this side of the molecule, let me go ahead and change back to black. So go over here to this side of the molecule. Again, we have methylene protons, so they're going to be chemically equivalent with each other, but they also share symmetry with our B protons over here, right? So if we speared this molecule and we rotated it 180 degrees, we would get the exact same set of protons over here, right? So this guy does have an axis of symmetry, and so because of that, B and B, because they're symmetric, are going to give rise to the same signal, right? So both sets of these are going to give rise to the same signal overall. They are also, or these sets of chemically equivalent protons are also equivalent with these guys. So same signal. And then using the same rationale, as we go out to the end here, these guys are also symmetric with our set of A over here because, again, that axis of symmetry essentially denotes the fact that these are homotopic protons. So these guys would also give rise to that same A signal. So these are all chemically equivalent protons because of that axis of symmetry. So same signal as A. Okay, so then finally, I'm going to erase this guy down here, our little axis of rotation. So note that there was an axis of symmetry there. We have a few more protons to look at. So we've got this guy down at the bottom, and then we've got these two over to the left, right? So this one and this one are again going to be chemically equivalent because of that axis of rotation, right? So if we rotated this 180 degrees, we wouldn't be able to tell the difference between this proton and this proton. So these guys are chemically equivalent. So HD are chemically equivalent. And then finally, I wish I had a better color for this, maybe gray. This last one, A, B, C, D, this last one, E, doesn't have like any type of symmetry with anyone, right? Like it's by itself, it's all on its own. It doesn't have like a symmetric proton up here or anywhere else in the molecule. So because of that, this guy is going to give rise to its own signal. So this is going to be its own signal, and we'll call this HE. So overall, we've got our A protons, we've got our B protons, we've got our C protons, we've got our D protons, and then we've got our E protons. So that is going to give rise to 5 separate signals in our NMR spectrum. Signals in NMR. Okay, so again, a couple guiding principles. For both of these, there was no chiral center, so methylene protons were equivalent to each other, but it depended whether or not the molecule was symmetric itself, whether or not they would be equivalent to other methyl protons, or methylene protons too. Okay, so we did this problem in class as well, so go ahead and give this a try on your own and then push play again and I will go through the answer. But you're looking for the exact same problem, right? We're looking for the number of chemically equivalent protons in each of these two molecules. Okay, I'm going to start with molecule, we'll call this 1 here. So same exact type of idea. I'm going to start on the left-hand side. So we've got 3 methyl protons out here. So we already talked about how methyl protons are chemically equivalent with each other. So this will form our first set of equivalent protons, right? So we'll call these guys signal A. And then same thing as we move in. We have methylene protons here. There is no chiral center in this molecule, so these guys are distinct with respect to each other. So these guys are chemically equivalent. We'll call them B. As we move on out here, so these guys are chemically equivalent with each other again. So we'll go ahead and call these guys, these guys, we'll call these signal C. And again, B and C are not equivalent with each other because C is directly attached to a carbon that's attached to an oxygen, whereas B is attached to a carbon that's attached to a carbon that's attached to an oxygen, right? So we're looking for the exact same electronic or chemical environment, and B and C are distinct with respect to one another, right? So they're going to give rise to their own signal. All right, so again, like we saw in that last molecule, there is symmetry here. So this is drawn in an awkward way, but we could redraw it if we wanted to illustrate the fact that this molecule is symmetric. It does have an axis of symmetry here. So again, if we rotated this 180 degrees, we wouldn't be able to tell that we rotated it. So because of that, these protons are also chemically equivalent with our C protons. So these guys are the exact same as C. And then these protons, this other methyl group or methylene group, is chemically equivalent with our B protons. So these guys are chemically equivalent with B. And then finally, these methyl protons on the end here, these are also chemically equivalent with our A protons on the other side of the molecule. Right, so overall, because of the symmetry in this molecule, we are only going to get 3 sets of chemically equivalent protons, or 3 separate signals in the NMR spectrum. Okay, so then finally, we'll move on to number 2, this final one down here. So I'm going to start over on the left-hand side. Again, we're looking for chemically equivalent protons. We've got a methyl group out here, and so we already know that methyl protons are always going to be chemically equivalent, so we'll call these guys A. Then we move on to an oxygen, so we don't have to worry about any protons there. And then we move on to a carbon that's attached to a methyl and a hydrogen. So we've got a couple of things going on here. We do have another set of methyl protons here. They are distinct from our other set of methyl protons, so these guys are chemically equivalent with one another, but again distinct from this set over here. And then we've got this proton right here, right? So this guy is by himself. He doesn't have any type of other partner. This is actually what we call a methine proton. So I'll just note that the CH with other stuff attached, this is called a methine, whereas these guys were methylene, and then these guys were methyl. So methyl, methylene, methine. So again, no partners for it. It's by itself, it's alone. So it's going to be its own little set of chemically equivalent protons. So we'll call this guy A, B, we're on to C. Okay, so then this other one at the very end here, we've got another methyl group. So we know methyls are chemically equivalent. This molecule does not have symmetry, right? If I cut it down the middle and rotated it, I would know that I rotated it. That oxygen would move over to the right as opposed to being on the left. So because of that, these guys are distinct with respect to each other. So these guys are going to be their own equivalent protons. So we'll call this our D set. And then as we move to that interior, to that methylene group, we have an H and we have an H, right? So again, we've said, okay, methylene protons are chemically equivalent to each other, but The only point where that doesn't hold up is when we have a chiral center, right? And so note that right now we do have a chiral center in that molecule. So because of that, this guy and this guy are not chemically equivalent. They are distinct, and they will give rise to their own separate signals. So instead of those two being equivalent, because of the presence of that chirality center, we do have a separate signal for what we'll call HE, and then a separate signal for HF, right? So for this one, we've got a set of A, we've got a B, we've got a C, a D, an E, and an F, right? So we have 1, 2, 3, 4, 5, 6 separate signals in the NMR spectrum. And again, for these guys, these are what we would call diastereotopic protons. If we underwent the displacement test, those guys would form diastereomers as opposed to enantiomers or the same compound. Okay, so I would make sure you guys know this before tomorrow and the quiz. There's always an internal standard that is added in to your sample, okay? And that internal standard is called TMS, right? So TMS is short for tetramethylsilane, which is this molecule that is given over here on the right. Okay, so this is put into every NMR sample anytime you do an NMR spectrum, okay? Now, what is the big thing about this sample, or this molecule, this TMS, okay? Number one, how many different protons are in this molecule? How many chemically equivalent protons would you expect from tetramethylsilane here?
Two.
So notice that we have a bunch of methyl groups, with all these methyl protons. They're all chemically equivalent with respect to one another. Why are they not all chemically equivalent with each other?
They're not?
They are,
Okay.
right? So because of that, all of these protons are chemically equivalent, so we only expect to see one signal from this molecule, okay? So we will only get one signal because these are all chemically equivalent protons, so one signal. Most importantly, these protons are extremely shielded, okay? Meaning that they have all of these electrons around them, meaning that those electrons are producing a very strong field that is opposing the external magnet. And so because of this, all of these protons are going to be essentially absorb light at the lowest frequency possible, right? So this is actually incorrect. It says higher. This should be at frequencies that are lower than pretty much everything that we're going to be dealing with in terms of organic compounds, okay? Because they are extremely shielded. Shielded protons, okay? So because of that, TMS is going to essentially establish our zero on our overall spectrum. So what you'll actually see when you look at NMR spectroscopy is you will get a signal for TMS, and that's essentially what we define as zero. Everything is measured relative to it, okay? Now, what are we actually measuring relative to it? Well, we're measuring the frequency at which we actually see absorbance, okay? All right, so now I also need to define one other thing. Let's imagine that we're looking at benzene, and we're looking at the protons of benzene, okay? For benzene, how many different signals would you expect to get out of this? So notice I don't draw any of the protons on here, but how many protons are there? There's 1 here, 2, 3, 4, 5, 6, right? Are they chemically equivalent?
Well,
Could we rotate them and tell?
no, we can't. You could
Rotate it, you wouldn't be able to tell the difference.
because of the bond.
You could reflect it. You could reflect everything. There's like an angle or plane of reflection pretty much everywhere in that molecule. So because of that, all of these protons, without anything on this, these are all equivalent.
Every single one.
Every single one of them, okay? All of these protons are equivalent, so they're going to give rise to one signal. If there is something else on this molecule, if we had like a methyl group here, that wouldn't be the case, right? The introduction of anything else on this molecule would make these non-equivalent, but because it's just a hydrogen, there's only one signal from this guy, okay? So now, let's say that we had benzene, and we put in our TMS, right? And we put it in our NMR spectrum, and we take the spectrum, right? What we find is that these protons of benzene, when we put it in the presence of TMS, are going to essentially absorb light at a frequency that is 2,181 hertz to the left of TMS, right? So we measure all of these things relative to TMS, okay? So we would have these protons, and they would be absorbing light down here, and this difference is this difference in frequency, this 2181 hertz, okay? Okay, so now the important thing to note here, and this is why we're, instead of measuring these frequencies and reporting these frequencies, we use something else that's called chemical shift, is that this frequency that we actually see is dependent on the size of the magnet used, okay? So in the most basic NMR spectroscopy instrument, whatever, we utilize a 1.4 Tesla magnet, okay? For a 1.4 Tesla magnet, that gives us an operating frequency of what is called 60 megahertz. So if we use 1.4 Teslas, we can expect to see this type of absorbance at around 60 megahertz of frequency, okay? Now, what happens to that frequency if we increase the size of the magnet? Because that energy difference gets larger as we increase to from, let's say, 1.4 to 7, what's going to happen to those frequencies at which we absorb light? They're also going to get larger, okay? So for a 7 Tesla magnet, that ends up being an NMR instrument that has an operating frequency of 300 megahertz, okay? So there's an issue here, right? If we're looking at benzene in this 300 megahertz instrument, we see a chemical shift relative to TMS of 2000 hertz, right? If we are instead operating in a 60 megahertz instrument, we would find only about 460 hertz worth of shift relative to TMS for the exact same molecule. We don't like that, right? Because again, what we're going to be seeing is going to be dependent on the overall operating frequency of the instrument, okay? So to kind of get rid of that, so that we can always be reporting the exact same number, no matter the type of instrument that we're using, we define what is called chemical shift, right? And so chemical shift, what we do is we take the shift relative to TMS in whatever instrument we're using, and we divide it by the operating frequency of the instrument, okay? So when we do that for our 300 megahertz instrument, we end up with a chemical shift equal to 7.27 times 10 to the minus 6. If we did the same thing in our 60 megahertz instrument, we plugged in our 460 divided by 60 times 10 to the 6, we would get the exact same 7.27 times 10 to the minus 6 for the exact same molecule, okay? So again, the only thing we're doing here is we're dividing it by the operating frequency of the instrument, which gives us the same number for the same molecule, which is what we would like to have, okay? Now, 10 to the minus 6, 10 to the minus 6, we don't like to deal with small numbers like that, so a prefix multiplier for 10 to the minus 6 is something called parts per million, ppm, okay? And so what we do in terms of chemical shifts, in terms of NMR spectroscopy, is we just get rid of this 10 to the minus 6 and we replace it with ppm. Okay? So when you actually look at an NMR spectrum, we're not looking at frequency down here. We're looking at chemical shift in terms of parts per million. And that's what you'll actually see when you look at the overall spectrum of the molecule. Okay, so now, when we look at the overall spectrum, again, now we can see, oh, well, this is our chemical shift, right? And so just a couple things to note about the way these signals are arranged. So down here at 0, this is our internal standard. This is our TMS, okay? As we go from right to left, we're increasing our chemical shift. That means that we're increasing our frequency, which means that we're increasing our energy, which means we're increasing our deshielding, right? Right, so the more deshielded a proton is, the stronger the magnetic field that it feels. The larger the energy difference, the higher the frequency. Again, in terms of our overall spectrum here and going from right to left, we're increasing frequency, we're increasing energy, and we're, again, increasing deshielding, okay? Okay, so, for example, and let me just note this, we're going to talk about in the next lecture the various things that are actually going to influence the amount of deshielding a proton or a nuclei is going to feel. But as we go from 0 over here to this spectrum, it's only to 8, but this can go to 12 or 14, we're increasing chemical shift, right? So that means that These protons down here are more deshielded, right? They absorb light at a higher frequency, meaning they have a larger energy gap than these protons up here, which have lesser parts per million, okay? So overall, these low parts per million in our chemical shifts, that tells you that those protons are fairly shielded relative to protons that have higher chemical shifts overall, okay? All right, so then the last little thing I want to mention here is sometimes people will use kind of like an old archaic way to describe protons, right? So they'll say things that are fairly deshielded protons that have these really high chemical shifts. They will call these protons downfield, okay? And then things that are shielded with these low chemical shifts, they'll call these upfield protons. And so what that upfield downfield has to do, which it doesn't make sense, downfield but you're moving to the left, it's just, it goes back to the old way that we used to do NMR spectroscopy when it was originally invented, and that was essentially you would hold your NMR spectrometer at a certain frequency, so the frequency would be constant, and then you would vary the magnet to bring these guys into resonance, right? And so originally NMR, you were kind of plotted in terms of the magnetic field as you were varying it, and that's where we get this idea behind downfield versus upfield. We're at a lower field strength versus and a higher field strength. Now anymore, we hold the magnet constant and we vary the frequency. And so that's what we're actually seeing. But again, this downfield versus upfield is just this kind of old archaic way to describe these various protons. Just note that if we're talking about downfield protons, these are going to have high chemical shifts. They're fairly deshielded. If we're talking about upfield protons, these guys have low chemical shifts. They're fairly shielded. They're fairly close to TMS, which is our standard, okay? Okay, so the question is, well, what's going to determine where things resonate in the NMR spectrum? What's going to affect these various chemical shifts? And we're going to talk about that in the next lecture, right? So right now, we're taking away the fact that we've got our NMR spectroscope, or our NMR spectrum. We're measuring everything here in terms of chemical shift. It's relative to TMS. Low chemical shifts are shielded protons, and then high chemical shifts are deshielded protons.